In this video, I'm going to review change of variables because we're going to be using it as we move forward to make our integrations simpler to perform. We've already been doing some change of variables. Anytime we change the order of integration or use substitution in order to simplify the integration process, we are making a change of variables. We've learned that we have to pay careful attention to exactly how the integrand changes and how the limits of integration change whenever we do change variables. In one-dimensional integrals, we had to change the limits of integration when we made a substitution. And in two-dimensional integrals, we have to carefully consider how the changes affect both the integrand and the limits of integration. We also have to consider how the order of integration might be affected. Each change of variables involves a transformation from one region of integration to another. So let's talk about transformations in the plane. In a double integral, a change of variables is a transformation that maps one set of variables uv to another set of variables xy. We can express this as xy is equal to t of uv, where t is the transformation function and it has two components, t such that x is equal to g of uv and t such that y is equal to h of uv. T takes a region in S that exists in the uv plane and maps it point by point to a region R that exists in the xy plane. We can express it as R is equal to t of S, and we call R the image of S under T. Here's an example. If I let S be the set of all points uv such that 0 is less than or equal to u, which is less than or equal to 1, and 0 is less than or equal to v, which is less than or equal to 1, and this is a unit square in the uv plane, we want to find an image of S in the xy plane under the transformation t such that x is equal to 2u plus v and y is equal to 2u. So I've plotted my initial region S, which is a unit square in the first quadrant of the uv plane. The point 0, 0 is at one vertex of my unit square. Under the transformation, I take 2 times 0 plus 0 and 2 times 0 to give me the coordinates 0, 0 in my xy plane. Then I look at the vertex located at 0, 1 in my uv plane, and I use the same transformation rules, 2 times 0 plus 1 and 2 times 0, to map this to a point with coordinates 1, 0 in my xy plane. Then I look at the point 1, 0 in the uv plane and put it through the same transformation rules, 2 times 1 plus 0 and 2 times 1, which gives me a point in my xy plane located at 2, 2. And finally, I look at the point 1, 1 in the uv plane and again use the same transformation process, taking 2 times 1 plus 1 and 2 times 1. This maps my upper right vertex for my unit square in the uv plane to the point 3, 2 in the xy plane. I also can solve for u and v in the transformation equations. Y is equal to 2u so that u is equal to y over 2. X is equal to 2u plus v, which means y is equal to v, and v is equal to x minus y. These equations will help me set my boundary for my new region and could help me map from the xy plane back to the uv plane. In my new region, I have a parallelogram that is bounded by the lines y equals 0, y equal 2, x minus y is equal to 0, and x minus y is equal to 1. I can sketch that parallelogram in as a shaded region in my xy plane. This is the image in the xy plane under the transformation t. I also want to mention one-to-one transformations. A transformation t from region S to region R is 1-to-1 on S if t of p is equal to t of q only when p is equal to q, where p and q are both in S. So what does that mean? P and Q are points in the region S. This tells us that when the point P is identically equal to point Q in region S, then the transformation of P into region R will equal the transformation of Q into the same region R. The coordinates in region R of both transformed points will be the same. Now you get to try it. Pause the video and find the image R in the XY plane of the region S, which is given by the set of all points UV, such that u squared plus v squared is less than or equal to 1, given the transformation equations x is equal to u and y is equal to 4v. Sketch both regions S and R, and when you're ready, restart the video to check your understanding. In order to find this image, I am going to first plot my region S in the UV plane. When I do this, I find that I have a disk that is bounded by a circle of radius 1 centered at the origin. Taking my transformation equations, x is equal to 2u gives me x over 2 is equal to u, and y is equal to 4v gives me y over 4 is equal to v. This means that u squared plus v squared is less than or equal to 1 will give me x squared over 4 plus y squared over 16 is less than or equal to 1. Looking at this equation, I see that my image is bounded by an ellipse centered at the origin with a vertical major axis of length 8. I'm going to plot that region where my major axis extends from -4 to 4 on the y-axis. This is my transformed region R. So this is a quick review of change of variables and transformations. Be sure and let me know if you have any questions.